So 7.1 says polynomial functions. In fact, thank you. All of chapter 7 is going to be solving polynomials. So anything with an x squared or something like that, we're going to solve. Okay? So a polynomial in one variable is just a polynomial expression where the coefficients are real numbers. And the exponents are positive integers. Okay, so that means no negative exponents, one variable, we only see one variable. We don't have any coefficients that are like square root of -9 or 3i or anything like that. Does that make sense? So they're real numbers and the exponents are all positive. The degree of the polynomial, if it only has one variable, is the biggest exponent. And the leading coefficient is the coefficient of the term with the highest degree. So, true mathematicians, or those cranky mathematicians, if you will, they always write it with the biggest exponent first in descending order, right? So the one with the biggest exponent would be our degree, and the number in front of that guy would be our leading coefficient. Now, do you have to always write it in descending order? No, so that's why you have to be careful looking for the leading coefficient. Okay, so look at number 1 there. It says state the degree and leading coefficient of each polynomial in one variable. If it's not a polynomial in one variable, tell me why. All right, so the first one I have is 7z cubed minus 4z squared plus z. All right, do we have one variable? Yeah, we're good there. Are the exponents all positive? Yeah, we're good there. Okay, so what's the biggest exponent? 3. And then what's the leading coefficient? What's the number in front of that guy? 7. Okay, look at letter B. It says 6, a cubed minus 4a squared plus ab squared. Am I in one variable? No, I got an A and a B, so I don't even have to say anything else. Because of that guy right there. Okay, how about letter C? 3c squared plus 4c minus 2c to the negative 1. Is that guy in one variable? No, we got a negative exponent. Remember that negative exponents make it move? So that guy would really be 2 over c, and that gets a little crazy when we go to solve. Okay, then I have 9y minus 3y squared plus y to the 4th. Is that in one variable? Yeah, it certainly is. What's my degree? What's my biggest exponent? 4. Now, this is the tricky one. My leading coefficient, if you want to write LC, I'm happy. It's 1, right? Thanks, Thomas. Be careful because the 9's out front. Okay? So he sort of looks like he's the leading guy. However, it's the coefficient in front of this guy. Now, if it would have been a negative 1 or minus y to the 4th, then our leading coefficient, you can have a negative. That's okay. Okay, questions on degrees and leading coefficients? polynomials in one variable. Okay. Number 2 says, find p of 4 and p of negative 2 for the function p of x equals 7x squared minus 9x plus 10. Remember that this is just function notation. I'm telling you it's a function. It passes the vertical line test. Think about this being like a y equals. That's a fancy y equals. Okay, and I want to know what's happening to my function at 4 and at negative 2. Or think about what would be the ordered pair, 4 comma what, and negative 2 comma what, if I plugged those guys in. Does that make sense? All right, so I'm just going to plug them in. So p of 4 means I'm going to replace everywhere there's an x with a 4. Oh, I couldn't do that. I didn't replace everywhere there's an x. Now I did. That's really awful to see. There, that's better. Now, remember your calculator knows the order of operations, right? So, if you trust your calculator enough, just throw that bad boy in your calculator. Make sure that you use plenty of parentheses. Remember, we're not doing anything with the left-hand side. We're just simplifying the right-hand side. There's calculators up front if you want to grab one. Help yourself. So you should get 86. That means the ordered pair 4, 86 is on my graph. Let's go check it out. So if I put 7x squared minus 9x plus 10 into my calculator and a y equals, and I push graph, I may not see a whole lot. There he is. He's way up there. He's a little parabola. But I could go look at my table. Hey, look at that. 4, 86. Okay, well, it asked us for 2. It asked us for a 4 and a negative 2. Be careful when you plug this one into your calculator that you use lots of parentheses, because it's negative 2 squared. You get 56? We still have it in our calculator. You could go look at your table if you want.
Would you just be able to get the answer from the calculator without having to do the work?
Totally. So on your worksheet, you could type those bad boys straight in your calculator. Or you could type it into your table. Like you could put it in your calculator and go straight to the table and look at it. I'm happy with that too. Yeah, so on your worksheet, it should be super fast. If you want to show me more steps, you're certainly welcome to, but you don't have to. Yeah, I'd be half tempted to just write that equation in my calculator and go to the table. Yeah. Okay, so we put a number in, we got a number out, right? But what about number 3? Or wait, before I do that, are you okay with this stuff? Okay? All right. What's different about number 3, though?
It's a variable.
It's a variable. We're putting a variable into our function. Think back to like elementary school, right? And you had your in and out boxes, and it had little funnels, you know, in and out. We put a number in, we get a number out. You put variables in, you get variables out. Okay? So if you put an expression into this guy, I'm going to get an expression out, and we just have to simplify it. Remember, we don't touch the left-hand side. We didn't do anything with the left-hand side here, so we're not going to do anything with the left-hand side here. Okay, so this one you probably have to show a little bit more work. So everywhere there's an x, I'm going to replace it with y cubed. Okay, so p of y cubed. So I have 2 times y cubed to the 4th minus y cubed to the 3rd plus 3 times y cubed. Okay, rewind your brains. Power to a power, what do I do with my exponents? Multiply, right? Power to a power, we multiply. So this becomes 2y to the 12. Minus y to the 9 plus 3y to the 3rd. Can I combine anything like terms? I got a y to the 12th, a y to the 9th, and a y cubed. So no, we're good. That's all we can do. So we plug him in and we simplify. So we put a variable or an expression in, and we get an expression out. Okay, let's try 4. I'm going to replace m everywhere I have an m with 2x minus 1. Whoa, there we go. So I have 2 times 2x minus 1, the whole thing squared, plus 2x minus 1, minus another 1. What about this guy? What do I have to be sure to do? There's 2 of them, right, Hannah? There's 2x minus 1 times 2x minus 1, so that means I have to FOIL. So be careful. Thank you. So this guy really means 2 times 2x minus 1 times 2x minus 1. Like that. Hey!
Good morning.
Good morning! We're just doing some polynomials, you know.
Awesome.
Do we FOIL that first or do we put the 2 in?
Let's FOIL it first. So we'll FOIL that and then we'll distribute the 2. Good question. Okay, so here we go. Let's FOIL. 2x times 2x. 4x squared. Awesome. 2x times the negative 1. Negative 2x. Negative 1 times 2. Negative 1 times a negative 1. Plus 1. Okay, now I got some minus 1s over here. I'm going to go ahead and combine those guys just to save myself some room. So plus 2x minus 2. There's lots of 2's going on in this guy. Okay, let's combine these guys. So I have 2 times 4x squared minus 4x plus 1 plus 2x minus 2. Okay, are you okay there? Now you can go ahead and distribute. So 8x squared minus 8x plus 2 plus 2x minus 2. This is like the problem that never ends, right? Keep going. Okay, now let's combine some like terms. So I get 8x squared, and then I have a minus 8x and a positive 2x. So I'm going to get minus 6x. And then I have a positive 2 and a negative 2, so they're going to cancel. So all of that to get 8x squared minus 6x. And you can leave it right like that. You don't have to FOIL any or factor anything out. We can just leave them straight like that. So it's a little more time consuming when we put an expression in. Okay, questions on function notation, plugging things in. You guys at home doing okay? Okay. Yay. Okay, so most of everything that we've done so far, in chapter 6 we talked about parabolas, you know, that sort of thing. So everything that we've done up to this point has mostly been x squareds, right? A power of 2 or a degree of 2. This chapter we're going to talk about what happens when that gets bigger than 2. So at the bottom of your paper here, I just want you to look at some of these graphs and let's make some generalizations. Okay. So this first guy right here, he's a constant function. He's got a degree of 0. That would be something like y equals 3. His degree is 0, right? He has no variable, so therefore he has no exponent. Or you could think about him as like 3x to the 0, right? Because anything to the 0 power is 1. Okay. This guy would be a linear function. So maybe something like y equals x plus 3. Okay, that's how we get lines. And then this guy that says it's a quadratic function, we can see is a parabola. This guy might be something like y equals x squared minus 3. I'm just throwing like equations in there. Does that make sense? Okay, so then this guy says he's a cubic function and he's got a degree of 3. So it might be something like y equals x to the 3rd. There might be more numbers, that sort of thing. I'm just throwing them out there. And then a quartic function, that guy would be like y equals x to the 4th. And a quintic function, a degree of 5, would be y equals x to the 5th. Okay, so look there at those guys and tell me if you see any patterns, or what do you notice?
The degree goes up one every time.
Our degree's increasing every time. Yeah? Shaina, what do you notice?
Every time the degree increases, the line will change.
Yeah, the line changes the direction that it goes, right? So first of all, in this guy, a degree of 1, he was pointing in opposite directions, and then I go to a degree of 2, and he all of a sudden did this. Okay? And then it went 3, and I did this, right? And then 4, he went back up again. Anything else? How many times do they cross the x-axis? The same amount as their degree, right? And what happens when it crosses the x-axis? Say it again, David. It could be. When we're doing parabolas. I heard it. JJ, what were you going to say? It's a solution, right? That tells me how many real solutions I can get. So this guy, he crossed once. I get 1 real solution, right? 1, 0, root, solution. Those guys all mean the same thing. This guy can have 2 real solutions. Does he have to have 2 real solutions? No, but the number of real solutions he could have is 2. This guy, the maximum number of real solutions he can get is 3. Does he have to have 3? No. He has to have at least 1, but he could have more. Okay, this guy could have at most 4 real solutions. Okay, so if it's got an odd degree, do you also notice too that it points in the opposite direction? A degree of 1 and a degree of 3, 1 goes up, 1 goes down. Degree of 5, 1 goes up, 1 goes down. Okay, here let's make some generalizations over here. So if it's an odd degree, the arrows go in opposite direction. Oh, you can't see that, I'm sorry. An even degree, arrows in the same direction. And the degree tells us the number of roots we're looking for. Or solutions. In our case, it crossed the x-axis those number of times. Okay, questions on any of that? Okay, turn the page because now we're going to talk about what's called end behavior. So, come on. Catch up. End behavior is the behavior of the graph as x approaches positive infinity or negative infinity. So as I get further and further away from the origin, what is my graph doing? That's really what end behavior is doing. Okay? So there's a whole bunch of stuff up here, but I don't want you to get bogged down in that. Think about positive infinity is up and negative infinity is down. Okie dokie. Positive infinity is also going positive direction. Negative infinity is going to the left in the negative direction, okay? All right, so these are just some examples of what can happen. It follows a pattern, okay? So, I don't want to discount the value of this, but I want you to think about what is your graph doing. If your graph is going up this direction, he's going to positive infinity. If your graph is going, your arrow is in this direction, your graph is going to positive infinity as well. If your graph is going down, he's going to negative infinity. And if your graph is going down here in quadrant 4, he's also going to negative infinity. So we're going to talk about as x goes to positive infinity, so think this is your x-axis. So as x goes to positive infinity, what's happening? And as x goes to negative infinity, what's happening as well? That makes sense? All right. Like I said, it follows a formula, and you just have to fill in the pluses or the minuses, okay? So, number 5 here says, for each graph, describe the end behavior, determine whether it represents an odd degree or an even degree polynomial, and then state the number of real zeros. So how many times it crosses the x-axis. All right, I'm going to write it down so that you can see the way that it should be. So we're going to say f of x. That means my function goes to, and then this is the part we're going to fill in, as x goes to positive infinity. And then we're going to say my function goes to either plus or minus infinity as x goes to negative infinity. That part doesn't change every time you talk about end behavior. Okay, so let's look at our graph. As my x's are increasing, is my graph going to positive infinity, or is my graph going towards negative infinity? Negative. Okay. As x goes to negative infinity, so negative infinity is this way, so as I'm going to negative infinity, is my graph going positive infinity or negative infinity? Negative infinity. Questions on that? So the only thing you're going to change is that green line. Does that make sense? That's the only part that changes when you talk about end behavior. So what does the graph do as we go to positive infinity? As the x's get bigger, is he going up or down? As the x's get smaller, is he going up or down? Does that make sense? Yeah. So think this part right here, Jillian, is like our x-axis is increasing. So as we're going to positive infinity along my x-axis. So as my x's get bigger, is my graph going towards negative infinity, or is my graph going up towards positive infinity? So this part right here would be as these guys are going to negative infinity. Does that help? Good question. Okay, so there was a couple more parts to this guy. So it says describe the end behavior. So we did that. Is this guy an odd degree or an even degree? Even. The arrows are going in the same direction. So this guy's an even degree. And then it says state the number of real zeros. So the number of times it crosses the x-axis. It's kind of hard to see. Does he cross the x-axis at all? No, that guy has imaginary roots. So this guy would be no real zeros. Okay, are you up for trying B on your own? Should we do it together? Let me start it. Let me fill in the blanks for you. So, my function goes to blank as x goes to positive infinity. My function goes to blank as x goes to negative infinity. Okay, try that. China. It doesn't matter. So you can, can't do that. You can switch these two guys if you want. It doesn't really matter. My brain just always does positive infinity first and then negative. But it doesn't matter. You can do negative first if you want. Yeah. Okay, so as my x's increase, where am I going? Positive infinity. As my x's decrease, and I'm going to negative infinity. Where's my function going? Negative infinity. Okay, what's your degree? Odd. He's going in opposite directions. How many times does it cross the x-axis? Once. Which means if this guy was a third degree, we'd have one real solution and two imaginary solutions. And yes, by the end of the chapter, we will find all of those solutions. This is my favorite chapter. Ray's looking at me like I'm nuts. But it's my favorite. Because I can give you any equation and we'll find all of the solutions. It's like perfect. It's like perfect math. It works. Okay, that was 7-1. Questions on 7-1? Are you okay if we cruise to 7-2 notes? Really, I just want to show you some things in your calculator. Because there's no homework with 7-2. Okay, so the big thing about 7-2 is, there's two things. The first one is the location principle. And the location principle just says, if my function is negative at A, and then positive at B, then there's at least one real zero between A and B. That's because there's a sign change in the f of x or the y values. Okay, now, sometimes words in math make no sense, right? Like, okay, cool, lady. But let me draw you a picture to help you understand that. All right, so here's my function. Say it does something like this. What if it says right here, this guy right here, I'm going to say this point right here is A. So this here on my graph, I didn't draw it very well, is f of A, or my y value. Is that y value positive or negative? Negative, okay? So it's saying if my y value is negative at A, but then I say somewhere over here like this is B, this is my f of B, and he's now positive, somewhere between there, my function value has to be 0. And if it has to be 0, that means I have a solution in there. I have a root. I have a 0, right? So if you go from a negative value to a positive value, somewhere in between there, it's got to be 0. That's a whole lot more sense than all those words, right? That's all that's saying. If you go from a negative y value to a positive y value, or a positive y value to a negative y value, somewhere in there it has to be 0 and it has to cross the x-axis. That's all that location principle says. Okay? Now, the only other thing that I want to talk about is the relative maximum and the relative minimum. So as our graph is doing this and switching up and down, think about parabolas, right? We had one minimum value or one maximum value. So we no longer have those as my graph changes. Okay? This guy right here has no minimum value and no maximum value, but if I look right there, he kind of has a minimum, right? And if I look over here, he kind of has a maximum, if I would have drawn it better. So we get these things called relative maximums and relative minimums. Think about them as peaks and valleys. Okay? So the relative maximum is a point which no other nearby points have a bigger y-coordinate. And a relative minimum is a point which no other nearby points have a smaller y-coordinate. He's the smallest guy around. Again, think about peaks and valleys. Okay, let's go ahead and graph number 2. Does it bother anybody that I skipped one? Okay. Let's graph number 2. So let's put this guy into our calculator. So I'm going to go to y equals. And then I'm going to put in x to the third. Make sure you get out of your exponent. Minus 4x squared plus 5. And then I push graph, so you should see something like that. If you're not, let me know and I can help you. If it looks a little crazy, do like a zoom 6. There you go. So that'll put it back. The zoom fit and a 6. Yeah. Okay, so let's go ahead and put this guy from our calculator onto our paper. How do I do that? Table, right? Second graph. Let's look at our table. And we're going to get some really big numbers because we're dealing with like x to the thirds, right? Okay, so I can't graph negative 3, negative 58, or negative 2, 19, but I have negative 1, 0. And before that, they're very negative. And then 0, I'm at 5. 1, 2, 3, 4, 5. I should probably make this graph bigger. 1, comma 2, 2, comma negative 3. And then 3, negative 4. and 4, I'm all the way back up at 5. All right, now that looks like a hodgepodge. So you have to sort of use your table and your noggin in the picture. Okay, now, I'm going to keep it on my table here so I can show you some things. That location principle said if I have a sign change in my y values, that somewhere between them I have a 0. So if I look at my graph here, well, this guy's nice because I have a, oh, don't tell me you piece of poo. Right there. See that guy? I actually have the 0. All right, so there I have a 0. But then I'm going to look through this guy and say, okay, where is there another sign change? Where do I go from positive y values to negative y values? All right, well, I've got 5, a positive 5, positive 2. Oh, all of a sudden, right there between 1 and 2, there's got to be a root. So between x equals 1 and x equals 2, there has to be a root because my y coordinates change signs. All right, and then I go from negative 3 to negative 4. That's not a sign change. But I go from negative 4 to positive 5. So there's got to be a sign change there. So I have 3 roots. One of them is given to me at 0, negative 1 comma 0. But then I have one between 1 and 2 and one between 3 and 4. Is that what we see in our graph? Does it cross between 1 and 2? Does it cross between 3 and 4? Yeah, it sure does. So that's that location principle working. Does that make sense? Okay, then it says, estimate the x-coordinate for which the relative maxima and relative minima occur. So all I'm doing is I'm looking around this guy right here, and I'm going to say, all right, the maximum is about at x equals 0. And then I have a relative minimum right there. That guy at x equals 3. Or around x equals 3. Now, remember, you could actually go find all of those things exactly. So we could go to our calculator and find those zeros exactly. We could go to our calculator and find the max and the min exactly. I'm not going to make you do it, but I just want you to see. Remember when we go to second trace, that calculate menu, if you wanted to find those zeros, this is where we were moving our spider, the left bound, right bound stuff. Minimum, that would be looking for that guy. Maximum, we would be looking for that guy. Do you want me to go through those so you can see them? Yes, okay. So let's start with zeros. This one we know crossed nicely, but let's go ahead and find this guy right here. So as you can see, I hit 0. So now it's asking me a question, my left bound. Are you to the left side of your 0? So for my graph, I want my spider to be left, right, because somewhere between these two lines is going to cross the x-axis. Okay, so there's my left side, there's my right side. So I put 2 lines in there from my calculator, and I'm going to push enter to guess. We said it should be somewhere between 1 and 2. Hey, look at that, it's 1.38. Okay, let's find the other one. Second trace, I'm going to go to 0. This time my left side is below, he's negative. My right bound is above, he's positive. So somewhere between those two, we said it should cross. Notice that's between 3 and 4. And the 0 is at 3.6. Okie dokie. So we found the zeros. I'm going to go back to that trace menu, and now I'm going to use minimum. And that means I'm going to be looking for that guy. So my spider needs to be on the left side of my valley. Right bound is on the right side. Yes, please, calculator, guess. It's actually at 2.66 and negative 4.48. It said estimate, so we're good, the x coordinate there. And then the other one I'm going to find is a maximum. So the left side of my peak. The right side of my peak. Yes, please, calculator, guess. And it should be, ooh, I'm glad this happened. Remember when it's got that E? That's scientific notation. That means it has 5 zeros in front of it. So that's essentially 0. So 0, 5. David, is yours not matching?
Your X has 1 point.
See the E?
Yeah.
That scientific notation? So it has 5 zeros in front of it. So it's 0, 0, 0, 0, 0, 1.
Just wondering why
It's just the algorithms in the calculator that do it. Yeah, did yours come up with 0 or did you? Yeah. So see, it might be different what it's doing in the background. Okay. Are you okay with 7-2? That was my plan, just to show you 7-2. Do you need to see more with 7-2? Okay, I'm taking it you're okay. So, turn the page one more time, and this should be your first homework assignment. You guys have to tell me if you like it this way better, okay? So far, so good. Okay, so on 7-1, this is the only worksheet you have to do today. So 1, 2, 3, and 4. If it's in one variable, just tell me the degree and the leading coefficient. If it's not in one variable, you have negative exponents, you've got 2 variables, you don't have to do anything but say not in one variable. 5, 6, 7, 8, 9, and 10. You're plugging in -2 and +3. You don't have to show me a lot of work on that. Okay? You can plug it into your calculator and look at the table, or you can just plug it into your calculator. I'm okay with that. 11 through 16, there's going to be a little bit more work to show because you're plugging in a function. If you have a number out front of your function value, that just means multiply everything when you're done by -5. Or on number 16, you're going to multiply your whole function by +5. And then 17, 18, 19, that's where you're going to do your end behavior. F of x goes to blank as x goes to +infinity. F of x goes to blank as x goes to -infinity. Tell me whether it's odd or even, and then the number of times it crosses the x-axis. Okay? All right. Let me push pause. Come on. There it is.